optics. In 1820, another Dane, Haroche, observed quite by chance that when the current is going through a wire, and he had a compass sitting near his setup because he was just doing a different kind of experiment, and he found each time he was connecting this wire to a Volta battery, which had just been discovered, and he found that each time there's a current through the wire, the needle of the compass is rotating. So he found that electric currents create magnetic fields. The news came to Paris in 1820, and André-Marie Ampère was fascinated by that, and he started doing experiments on his own. You see here, this is a setup of Ampère, which you can find now at the Collège de France. Ampère was a professor at Collège de France in the 19th century, but he did not do this experiment at Collège de France. This experiment was done at his home, which was, I think, Rue Monge, very close to the Collège de France. We're just sending currents into two wires and measuring the force produced by the currents on each other. The fact that the current creates a magnetic field, and the magnetic field reacts on the current. And so it was a lucky time when you could do fundamental physics at your home with a very small amount of money. But of course, you had to be someone like Ampère or like Faraday, who was doing similar experiments in London at the same time. What Faraday did was to look at what happens when you have a solenoid with a current and you just bring it into another solenoid. So what you do is that you are modifying, changing in time the magnetic field seen by a current. And this produced a transient electric field which drives the current in the second circuit. This is called induction. And it is the fact that varying magnetic fields create transient currents, and this is the basis of all electrical motors and the modern, of course, modern industry and modern technology. So you see that Ampère and Faraday found that there was a connection between magnetism and electricity, that varying magnetic fields create currents which are produced by electric fields. And there was something missing. In Ampère's equation, there was no varying electric fields. And Maxwell, who started looking at that, tried to make Ampère's equation more looking like Faraday's one. He tried to introduce another symmetry, which said that even if you don't have currents, by varying an electric field, you produce a magnetic field. And by adding this term, he gets a set of coupled equations, the one which is called the Faraday equation and the Ampère-Maxwell modified equation. And this led immediately to the fact that varying magnetic field produce an electric field, which in turn produce a magnetic field and so on. And that these two fields, which are here shown in blue and in red, propagate in space. And this was called the electromagnetic field. So this was a great discovery by Maxwell. An important parameter for a field is, of course, the wavelength, the distance which separates two crests of the field. And this wavelength was also, so we'll come back to this wavelength in a moment. I show you here the page of Maxwell's manuscript where he described this effect in 1865. This is a manuscript that you find at the Royal Society in display in London. And it is, I think it is maybe one of the most important piece of writing in the history in general, because at the bottom of this page, he says that light is an electromagnetic field. How did he come to that point? Maxwell's equation gave him the possibility to compute the velocity of this phenomenon. And what Maxwell's equation said is that the velocity of the electromagnetic field was inversely proportional to the square root of a product of two quantities, epsilon, which is the electrostatic constant, which comes from Coulomb's law, the law which describes the attraction or repulsion of two electric charges, and mu was the parameter introduced by Ampère to describe the effect of currents on each other. And by taking the product of epsilon and mu, taking the square root and the inverse of the square root, he found a value for C, which was a value that Fizeau had found in his experiment. So at the end of this page, and I just read it for you, but you can read it in Maxwell's writing, the agreement of the results, these two measurements, the value he found and Fizeau measurement, seems to show that light and magnetism are affections of the same substance, and that light is an electromagnetic perturbation propagated through the field according to electromagnetic laws. So this sentence is really one of the most important sentences in the history of science. And I am rather proud to note that the values of velocity of light that Maxwell shows here are in kilometers per second. And when you go to England and look at the textbook now, they say that light is going at 189,000 miles per second. So you see that Maxwell was already ahead and used the metric system in science. So this was really a fantastic discovery. Light is an electromagnetic wave, so you have different kind of light waves depending on the wavelengths. And what happens is that the visible light, the light to which the eye is sensitive, has wavelengths in a very narrow window. 0.4 microns is blue, 0.8 micron is red, and you have, this is a visible spectrum. But below, for longer wavelengths, that is smaller frequencies, you have the infrared, microwave, and radio waves, which were not observed. And at higher frequencies, smaller wavelengths, you have ultraviolet X-rays and gamma rays, which were not observed. So you see that Maxwell's equation predicted invisible light, light that nobody had seen the effect of. And about 10 years after the death of Maxwell, Hertz observed radio waves. He used an electrical circuit making sparks, and he saw that these sparks were producing waves which were detected by an antenna. And this was, of course, the beginning of radio broadcasting. And also, these radio waves are of the same nature as the cosmological background radiation, and they're also of the same nature as the waves which are detected in nuclear magnetic resonance in the MRI medical imaging technology, which use the micro radio waves that the spins in our body, the magnetic moments of the nuclei in our body emit by when they rotate in a magnetic field, and this is very important, of course, for medicine. At the other part of the spectrum, 10 years later, Röntgen discovered X-rays, which are penetrating bodies and which are also very important for analyzing what happens inside our bodies and also to analyze materials, crystallography, and so on. So it's very, very important. And one can say that this was a giant technological leap. But what I want to stress is that it also was very, very important for fundamental and theoretical physics, because questions about the nature of Maxwell's equation, what they really meant, led to relativity and quantum physics. And so, first of all, relativity. Maxwell's equation tells us that light is propagating at 300,000 kilometers per second. But of course, when you give a velocity, you have to say what is the reference frame. In which frame light is going at this velocity? So Maxwell assumed, by writing his equations, that there was a preferred frame in which light had this velocity. And so the young Einstein immediately asked himself the question, but what happens if I move in this frame? If I move along the light beam, will I see the light beam going slower? And if I move at 300,000 kilometers per second, will I see light motionless? And what does it mean, according to Maxwell's equation, to have a motionless light beam? And it had no meaning. So in order to understand that, Einstein looked back to another person that we heard about, Galileo.